We're starting our topic of literal equations with this alike and different. So within an alike and different, we're looking for things that are the same, things that are different. If you'd like to pause and think about some on your own, you can do that, and then I'll go through a few ideas. So we see things like there's a square here and a square here, so those are alike in that way. We see that some of them have a single thing on the left, like A, B, and D have a single letter on the left, whereas C has two letters on the left. We see there's capital letters in all of them, in all of them, so they all have that in common. B has this subscript or this label with L, which is weird and different. A, B, and D all have Greek letters in them, which is a thing they have in common. And then an important thing they're all alike in is that they're all formulas. So they're all things used in math and science and engineering in order to solve important problems in people's jobs and in the world. So it's a different example. We're looking at this equation that says flower times heart plus star equals smiley. Remember that when we write two things back to back like this, there's always a hidden multiplication operation, and that applies whether they're letters, numbers. If I write x, y equals 8, that means x times y equals 8. So there's always a hidden multiplication in there, and you can write it as a dot or as parentheses, whatever. Dot is probably clearer here. So if we wanted to solve for this heart shape, then we're going to need to get the heart by itself. Remember that solve means to isolate or get that thing by itself. So identifying the operations here, we have an addition of a star and a multiplication of a flower. And just like any of our solving that we've done, we're going to undo those in reverse PEMDAS order. So first, we're going to do minus star from both sides. So star and smiley face are different kinds of things as far as I can tell. They're not like terms, like they're not the same shape. So now I have, flower, flower times heart is equal to smiley face with a uni-eye, maybe he's a cyclops, minus star. Okay, next we have this multiplication, so we need to divide by this flower that I'm no good at drawing. Flower. Great. We need to divide both sides by that, because this one we need to cancel. And then we're left with the heart on the left is equal to the smiley minus the star divided by the flower. And this is another spot I want to bring up something called equivalent expressions, because it's so important to understand. And that is the idea that here I divided everything by the flower. So I divided this entire thing by the flower altogether, but I could also have written it as smiley face over flower minus star over flower, and it means the exact same thing. These two are what we call equivalent expressions. So this one and this one mean the same thing. And recognizing that and understanding that those are two ways of writing the same thing is going to be really important for this section, and it's one of the most important things to really getting higher level math. All right, literal equations. So literal equations are generally thought of as formulas, but they are really just an equation with multiple variables. So even if it's not a real life formula that somebody uses in math or engineering or science, then that's okay. It's anything. So if I just wrote A, B plus C equals D, that's nothing meaningful, but we'd still call it a literal equation because it has multiple variables in it. Facts to remember. Solve means to isolate. What else? You can solve for any variable. So that's the idea of this section, is that we just solved this for the heart. It started out solved for the smiley face. The smiley face was already isolated. I could have also solved for the star or the flower. So I can solve for any of those variables, and it's fine. Like, there may be cases in which I want a different one by itself, and that's the skill that we're learning here, is how to solve for any variable within that literal equation. So a equals pi r squared was one we saw earlier. So if I wanted to solve that, right now it's solved for a, it's giving us the area. But what if I wanted to solve it for r? I could rearrange it by, we're probably going to have this as an example later, but whatever. So I have a multiply and an exponent. So I need to deal with multiplying first. So I would put a divided by pi. And then I need to square root both sides, so I would put a square root over that and say that is equal to r. So we can rearrange any equation for any variable in general. Other examples, area equals length times width. I don't know, I'm just really on geometry today. You get the idea. Non-examples. X equals 4. That's not an example. Yeah, it's just would be if you don't have multiple variables. So, like it says here, these are often real-world equations that have values, so we're going to look at some of those. Here we have area of a rectangle. Area is equal to length times width. So A is area, L is length, W is width. We could also say base times height instead of length times width. It would be the same. So if we want to solve for L, we have A equals LW. If we want L by itself, the operation taking place here is multiplication. So to undo that, we would divide by W, and we would get L equals A over W. And there we go. Solving for W would be the exact same process, so I'm going to leave that one for you to do. I'm probably just going to do one on each of these and let you do the other one. So feel free to pause and do those to make sure you're getting it. Perimeter of a rectangle is, so P is perimeter, L is length, W is width. Solve for L. So we have P equals 2L plus 2W. So here, identifying our operations that have happened to L. L is our focus. That's what we want by itself. We've multiplied and we've added something. So in our reverse order of operations, we would first subtract 2W from both sides. We get P minus 2W is equal to 2L. Now we need to divide by 2. And remember, like I said before, there's two ways to represent this. I can divide both sides by 2, or I can divide each term by 2. And that would lead to the answer looking slightly different, but both are correct answers as long as L is by itself. So in this case, I'm going to do P minus 2W all over 2, and that gives me L is equal to that, P minus 2W over 2. But if I divided each of the individual terms by 2, I would get L equals P over 2 minus W. So that would be 2W over 2 and then simplify to just W. And these two are equivalent expressions. So they are the same thing, and either one is okay, and understanding they are the same is just really important. W is very similar, so I'll leave that for you to do. Potential energy. What about an unfamiliar formula? So they give us the definitions here. Potential energy is mass times height times acceleration. Acceleration due to gravity. I would call that gravity, but okay. So solve for m. So we have P equals m times g times h. So this is basically looking like we have m times g times h. But both of those multiplications are times m. So rather than dividing by g and then dividing by h, what I would do is divide by g times h. Because you could think of this as being m times g times h, all together, group them together, and divide by that all at once. Then we get m equals p over gh. That's more efficient than dividing separately and doing divide by g, then divide by h. So I'll leave g and h to do for you. Volume of a prism, rectangular prism, so this is volume. And then we have length, width, and height, which I can't spell while I'm talking. Length, height. Solve for L. I'm actually going to do solve for W on this one because it has more space, but this is going to be very similar to the last one. So L times W times H. Again, I'm going to think of this as W is being multiplied by LH. So I don't need to write this, but just to explain how I'm visualizing it, W times LH. So then I'm going to divide both sides by LH. And I end up with W equals V over LH. And then I'll leave the other two for you to do. Again, they're very similar to the potential energy one. Velocity. So we have velocity, we have distance, and we have time. If we're solving for D, then we have V equals D over T. The operation happening to D is a division operation. And we know that to undo division, we multiply both sides by T. So we have D equals, typically when we have multiple variables together like this, we put them in alphabetical order. So I would put TV. But if you put VT, it would be equivalent. But if we don't know what order to list variables in, we typically list them alphabetically. T is a little different, so I'm going to go ahead and do that one as well. So we have V equals D divided by T. So this one is a division, but our problem is that T is in the denominator of this fraction. Since T is in the denominator, the only way to fix that is to multiply both sides by T. So we're going to multiply by T, just like we did in the last one, and we get D equals T times V. And now, to get T by itself, there's a multiplication operation to undo. So I need to divide by V to get T by itself, and we do T equals D divided by V. So that one, anytime the variable you're solving for is in the denominator, you have to multiply by that variable in order to get it up to the top. Your work will never be done unless it comes up to the top. So a different way of framing that, which I don't prefer, is to say, to use cross multiplication, which is an unnecessary thing to do here. So if I wrote this as V over 1 equals D over T, and then cross multiply, V times T would be on the left, and 1 times D would be on the right. And you'll see that I get the same exact result as what I got doing it the other way, but it's hiding behind this trick of cross multiplying, and it doesn't show like understanding the same way that multiplying by T does, in my opinion. All right, area of trapezoid. So we've got area, we've got base 1 and base 2 and height. So here's a place to point out this B1 and B2. So these are called subscripts, and they are basically labels. So they're just naming the thing. Since there are two bases, you may remember a trapezoid has two different bases that are different lengths. So in order to differentiate them and say one of them is one thing and the other is the other, we put a subscript, which is a little number down below the letter, and it's not anything mathematical. It's literally just a name saying that this is base 1 and this is base 2. So you may have seen that in the alike and different. We had way back up here. Wow, way back up here. We had that in B. So we had this L sub 0, and we call that L naught, which means initial length, the length before anything happens. Initial, again, I can't write while talking. Initial length. So before anything happens in this problem, that's where the length was at first. So anytime you see a little number down below a letter, we call that a subscript, and it's labeling that as a certain one. We actually also use that from our previous topic in function notation. So where we said f of 2 equals something, we could write that f2 equals something. So you can read subscripts in function notation as blank of blank, like this would be f of 2. And that'll come up more when we get to sequences in a little bit. Solve for B1. So we got a lot going on here. We have this trapped in parentheses, so we can't touch anything in there. We have this multiplication, and we have this multiplication. So first thing I would do is remember, let's reframe that last one. Let's call this a division instead of a multiplication. So we're dividing by 2 there. So we have a multiply and a divide to deal with. I like dealing with the division first, so I would do A equals 1/2 B1 plus B2 times H, and then I would multiply both sides by 2 to get rid of the 1/2. So at that point, I'm just going to write over here in this blank space, so we're going to go down here, 2A is equal to, still in parentheses, B1 plus B2 times H. So we still have a parentheses and a multiplication to deal with. So let's divide by H to get rid of the thing that's keeping the parentheses intact. So now we have 2A over H equals, and then with the H gone, these parentheses are no longer necessary and they collapse. So B1 plus B2. And then since we're trying to solve for B1, sometimes when I'm first starting on this, I like to highlight what I'm solving for throughout the problem so I don't get confused or lose track of it. So now what I need to do is subtract B2 from both sides, and I get B1 is equal to 2A over H minus B2. And that would be the answer to that, solving for B1. And then I think the other two on this one you can do on your own. Is there anything else I wanted to say? Oh yeah, so one other thing I wanted to say on that one was the first way I wrote it had the 1/2 and the H both as a multiplication. So looking at, I'll just write over here. So what if we said this was H over 2 times B1 plus B2? Like both of these H and 2 were together multiplying by B1 plus B2. Then we could take a shorter path to the solution by multiplying by the reciprocal of H over 2. So H over 2 would become 2 over H, and we'd multiply by that on both sides. The H would cancel the H, and the 2 would cancel the 2. And that would get us an extra step, so that's 2A over H. And now the parentheses are gone in one step instead of 2 steps. And we get the same answer. It doesn't matter which way you do, but recognizing things like multiplying by a reciprocal could save you a step here or there and make things more efficient. area of a triangle, I think we've covered well enough for, I feel like the last one I might want to do here is volume of a cone, because solving for r, we're trying to solve for something that has an exponent applied to it. So we'll do volume of a cone and probably wrap up there. There are many of these to practice, so I'll leave the rest for you to practice, and we'll do both parts of volume of a cone together. So this is volume, radius, and height. Okay, so solving for r, our operations, we have an exponent, and we have a multiplication, and a division. So here I'm going to deal with the two multiplications together and the division by itself. I could again do a reciprocal. I could put pi h over 3 and multiply by the reciprocal, but I think that's a little more advanced, so I'm going to not do that here. So we're going to do v equals 1/3, and put r squared times pi h. Again, you don't have to write that. I'm just showing you I'm thinking of pi and h together because they're both multiplying. We're going to divide both sides by pi h. And then on the left we have v over pi h equals 1/3 r squared. Next we need to get rid of this division by 3, so we multiply by 3. And remember that 1/3 is the same as divide by 3. They mean the same thing. So now we have 3v over pi h is equal to r squared. And then as a final step, we need to square root both sides. So we'll square root both of those and get r equals the square root of 3v over pi h. All right, solving for h, the thing I want to point out with that is that it doesn't matter that the r is squared. So if I'm solving for h, I have this divide by 3 and this multiply by pi r squared. It doesn't matter that the r is squared, that's just some stuff times h. So as a first step, I would multiply by 3 to get rid of the division. 3v equals pi r squared h, and then I would just divide by this stuff that is times h. So it doesn't matter what it looks like, I just divide by that thing. So divide by pi r squared, divide by pi r squared, these cancel, and I'm left with h equals 3v over pi r squared. So we'll go ahead and end today's notes there and leave the rest for you to practice. Hopefully this is seeming not too intimidating. Like, it's not that hard to move the things around as long as we just identify what operations we're using and then use our normal equation solving skills to undo those things.